Hello. So let us start the new episode of the solid state physics course. And here, what I'm going to talk about is similar to what I talked about. So I made a video about what is the equivalence between Bragg's law and Lawe's condition. But I think that like there are some points or there are some more improvements that could be made, and there are a little bit of clarification needed to be given to the concepts that I actually talked about in the last class. So I will talk about the same things in the last class. I wanted to make this video on the same topic once more so that you can actually get a more clarified view of what is going on, because I think some technical terms are needed, and also more nuance and more technical details are needed to uncover what is the true mode of comparing the Lawe's condition and the Bragg's law, and how crystallography is actually related to Bragg's law and how crystallography is used. And we will also kind of study a little bit about crystallography and how to actually extract data. And like I think interspatial um, distance is a very good measurement, or a very good thing, or a very good parameter that people generally find out through experiments. But I think that crystallography data will tell us a lot about the atom, and also the lattice spacing, and also the structure, and it also has some physical insights that actually we can extract very nicely. So I think, yeah, we are going to talk about those things, and um, that is a very good uh, way to start about the things. So let us actually start. So okay, so again we are basically talking about the reciprocal lattice vectors. So it will be a little bit of a longer video, reciprocal lattice video. So what I am going to talk about is that the same thing, Bragg's law. So let us actually go back to Bragg's law and something which is very important in crystallography, and that is called Miller indices. So Miller indices are everywhere in crystallography. So for to understand crystallography and to analyze the graphs that you get, so like we have to think about also as a like experimentalist and also as a theorist. So the theorist part of us will tell us that okay, we have this Lawe's condition, we derived this Lawe's condition through like complicated integrals and stuff. And also there is an experimentalist side of us, we who just like sees some in crystallographic data, and it has some data, it has some experimental data, and now how do we correlate these two things? So I just told you about the lattice spacing and how the Lawe's condition and Bragg's laws like are related. So I am going to start from the experimental side today to see that okay, these are the data points we get, these are the kind of data we get, and this is how we can mathematically come to a conclusion about it, how we can mathematically analyze that. So let us go back to the Bragg's law. So this is Bragg's law. We have like some atoms. This is obviously a model, but what is happening in reality is there is a sample, there is light, um, there is light which is coming to the sample. The sample is actually rotated with an angle theta. So there is an angle through which the sample has been rotated with respect to the horizontal, and the light is being diffracted in such a way that it's making an angle 2 theta. So this angle is theta and this angle is 2 theta. Okay. So, and what we will do is the machine will actually rotate the sample from 0 degrees to 90 degrees, and basically the theta will be, now rotate from 0 degrees, 2 theta will rotate from 0 degrees to 180 degrees, and we will see what kind of peaks we get. That's it, that's the experiment, and that's from that we will get some data that we have discussed about in a like very superficial manner in the earlier episodes. And I think that we just discussed that we just have some peaks. We have like a I versus theta graph, where there is a theta and there is an I, and we just have some peaks at certain thetas, and those thetas are supposed, like they are like supposedly some information, uh, there there is some information out there in which thetas you get the peaks. So that will depend on the Bragg's law, as we talked about, that basically says that if this is the lattice spacing, then 2d sine theta equals to n lambda will give you the thetas where you have the peaks. So lambda is the wavelength of the light, wavelength of light. N is some multiplicity. Theta is the peak angle that we are getting. The like angle thetas are the angles where there is constructive interference due to diffraction, and D is the lattice spacing. Now this lattice spacing is lattice spacing, and it does not tell us anything about lattice parameters. So that is what we are going to kind of discuss in this class, because I think it's very very important to like draw a parallel between Lawe's condition and Bragg's law. So okay, now let us talk about Miller indices. Miller indices, and there are lattice planes, Miller indices and lattice planes. Okay, so what are lattice planes? Lattice planes are exactly the thing that we discussed just like now. That there are lattice planes where the diffraction is happening. So there is this lattice plane, the light is coming, light is going, light is coming, light is going. So this is exactly the lattice plane. So this is the plane. For example, this is the pink line is the plane. This pink line is another plane, and D is basically the perpendicular distance between the two planes. That's it. So we now think about how we can construct lattice planes into a lattice, because if you have a lattice with a lot of atoms, there can be multiple ways or multiple angles, multiple orientations of the planes that you can construct. So basically, um, what we will do is, let's say we start with a real lattice cube. So it's a cube. It's not a cube. It's basically a unit cell for the real lattice. It's a 3D unit cell. So let us make a unit cell, right? And now what we are going to see is that, let's say this is the vector A, this is the vector B, this is the vector C. So this is the x-axis, this is the y-axis, this is the z-axis. Now we are going to see that, okay, for fine, this is a unit cell, but we don't know what is the basis. We talked about earlier that a crystal or a crystal object is made up of cells, the lattice parameters or the lattice vectors, and also the basis. So let's say we have some atoms here. Let's say it's like some face centered cubic, something like that. So we have also atoms in the corners, we also have atoms in the faces, right? So now, because there are multiple atoms in the unit cell, it's not a simple cubic thing. So we can actually, if you can think about it in a more geometrical way, we can make a lot of planes through these things. So basically what we are going to do is, we are kind of seeing that how can we specify a plane. So let's say there is a plane which is cutting through this cube. So we need some language to specify the plane, that what are this, like the parameters of the plane, sub parameters we need. So that is what we are kind of looking into. For example, we have this plane, a plane which cuts through the cube like this. Okay, so this is a plane. This obviously extends beyond this unit cell because it's periodic. It has a periodic boundary condition and it's an infinite solid. But due to this plane, we have like this is infinite, but it cuts it through the unit cell at certain places, at certain lines and certain points. So one way we can categorize this plane, maybe this is a plane, but how do we kind of quantitatively say that, okay, this is a plane? For example, in 3D geometry in mathematics, we have an equation of plane, we have an equation of a line. So similarly, we want to have some sort of an equation of this plane with respect to the lattice vectors. So the way we do it is we can see that it intersects the A or the first x-axis. Here I am talking about an orthorhombic unit cell, but that is not something which is necessary. It might not be the case. So let me, yeah. So orthorhombic. So this is an orthorhombic, for example, I am taking, but it might not be. So what I'm trying to say is, for example, the A or the x-axis lattice vector, it is the plane is intersecting the A at A by 1 actually. So how much distance from the origin? So this is the origin. The dark blue point is the origin. So from how much distance from the origin is the plane intersecting the x, y and z axis? Or in more general case, how much distance from the origin the plane is intersecting the lattice vectors? Here the lattice vectors are x, y, z because it's an orthorhombic, but it might not be. Okay, so it's we can see that the plane intersects the lattice vector at a distance a, the x lattice, the first lattice vector, and it intersects the second lattice vector at also b by 1. Then we have c by 1. So we can say this plane is 1 comma 1 comma 1. This is the Miller index of the plane. That's how we categorize and label. Basically it's a labeling of the plane. So that's how we categorize or label the planes. Okay, so that is something, and we can actually now we can see about like more examples. We can have more examples. Let us get a little bit of hang, or let us get a little bit familiar with what we are doing here. Okay, so this is another orthorhombic cell, and I'm going to draw another plane which looks like this. Okay, so now we can see that it has an interesting feature, that it cuts the first axis A, not at A by 1 but at A by 2, same for B, B by 2 and C by 1. Okay, so this is the index of the plane will be 2 to 1 for the Miller index. Now we can see that this plane has some relation with the reciprocal lattice vector. Okay, so the reciprocal lattice vector, so for example we define three vectors here. So what we hypothesize is that the reciprocal lattice vector is actually gonna be perpendicular to this plane. So that is what is going to happen, but we need a proof for this. How we can prove? We can prove that, let's say there is a g vector, and this Miller index will have some connection to those, how to construct those g vectors. So g vector is a reciprocal lattice vector which is a linear combination of the primitive reciprocal lattice vectors, the primitive, the unit cell or the lattice vectors of the reciprocal unit cell, right? So mn, let's say k, correct? So a star, b star, c star are the lattice vectors of the reciprocal lattice. And so let us do one thing. If, for example, this is vector p, this is vector q, this is vector r, and what we want is g dot p equals to 0, g dot r equals to 0, and also g dot q equals to 0. Okay, so if we do that, so p is what? P is a by 2 minus b by 2, q is c minus a by 2, r is b by 2 minus c. If we actually put the g into this equation, so what we will get is basically m equals to 2, n equals to 2, and k equals to 1. So g for the plane g perpendicular to the plane, which has a Miller indices of 2 to 1, it can be given as 2a star plus 2b star plus 1c star. So that is the fascinating connection between the reciprocal lattice vector and a plane having a certain Miller index. So as we can see that there is a relation between the Bragg's law, which deals with the interplanar spacing, and it deals with not lattices but basically planes. That has a connection with a g vector which is indeed perpendicular to those planes. So that kind of gives us some hint that okay, the Lawe's condition and the Bragg's law, they might be having some commonalities. So um, again, so the statement that we kind of got, the result is the vector g equals to h a star plus b, sorry, a, k b star plus l c star is perpendicular to the plane having Miller indices h k l. So that is the important result that we got out of our exercise. Now we are going to build upon this result. So these are some planes, right? And there will be multiple such planes. So that is the point, because this is one plane that was for one unit cell. But the same thing can be done because there will be another plane, another unit cell here. So there will be a plane like this. So there are in principle infinite number of planes, and we want each of them to interfere constructively. So let's say the perpendicular distance between them is hkl. d perpendicular distance between two planes having Miller indices h, k, and l. From the Bragg's law, we saw that 2 pi 2 pi sine theta equals to in lambda. Okay, so I think there was a little bit of error maybe. Yeah, so it's 2d sine theta. Sorry for the mistake. So it's 2d sine theta, 2d hkl sine theta. Now we are going to give it a meaning. We are going to give it a label, because now we know that in a lattice there can be multiple such planes. So for example, there can be 1 1 1 plane, there can be 1 1 0 plane, there can be 1 2 2 1 plane, there can be 2 1 2 plane. So there can be a lot of planes, and due to those lot of planes, in reality what happens is for every sample you might have uh, like a powder. Generally how we do experiments, how the experimentalists do experiment, is they take a powder of a sample so that they are oriented in a lot of ways. So for example, you have a powder, you have a crystal like this, 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 you have a crystal like this. You have all sorts of orientations possible. So you will have a very good probability of shining light such that it is perpendicular to this plane, or in some crystal it's perpendicular to this plane, or in some crystal it's perpendicular to this plane. So all of the planes will get, you will get the data from all of the planes. So what we will do is we take a general plane which has a Miller indices of h, k and l, and we do d h k l 2d sine theta equals to n lambda. Okay, and now we are going to go to the lowest condition. What was the lowest condition? K prime minus k equals to g, or without even the this sign we can get k prime minus k equals to g. Now let us draw again the interplanar spacing. So this is, there are two planes. This is DHKL. Rays are coming, um, and also rays are going like this, right? So what we can see here, uh, let's say this is K, this is K prime, and this is theta. So then we can immediately see that the K will have a magnitude of 2 pi by lambda, where lambda is the wavelength of light. And so if you see, what will be the thing is, it k prime will be 2 pi by lambda into cos theta x cap plus sine theta y cap, and k will be 2 pi by lambda into cos theta x prime x cap minus sine theta y cap. So if you do k prime minus k, then what you will get is very clear. I will get, so k prime minus k, even if you take the mod, it will be 2 pi by lambda into 2 sine theta. So the y cap is gone, and that is equal to g. But from Bragg's law, we also know that 2d sine theta equals to n lambda. dhkl sine theta equals to n lambda, right? So these are the two equations, and how to get, and we also told that g vector is perpendicular to the interplanar spacing, right? We already discussed that g vector, like g equals to h a star plus k b star plus l c star is perpendicular to the, what, this hkl plane, the plane having Miller indices hkl. Now we can see that if we compare these two equations, so what we get g, um, so 2 sine theta. If we compare 2 sine theta, right, you will get that 2 sine theta from this equation is what, n lambda by 2 dhkl, right? Not 2 dhkl, dhkl. So 2 factor is always, so 2 sine theta is n lambda by dhkl, and it, so this is 2 sine theta and 2 pi by lambda. When it cancels out, what we see is, you see that it is 2 pi n by d hkl. So this is an important result, that we are seeing that not only this g vector is parallel to dhkl, and they, dhkl and g both are perpendicular to the planes having a Miller index hkl, and the g and the d, they are actually related by this relation, where n can be any integer. So this is a important relation. So this again tells you the, um, it can it can tell you that it is quantized. The G vector is quantized, and it can only take integral multiples of this thing, 2 pi by d HKL. And this will help us actually to go and see how do we read crystallographic data, and from that can we actually get something, can we actually get some like information about what is DHKL. And now the thing is, another thing is, we know that G is what? G is H A star plus, sorry, K B star plus L C star, right? And what we know? We know that A in dot A star equals to 2 pi, B star equals to 2 pi, C star equals to 2 pi. But if you do A dot B star gives you 0, A star dot B gives you 0. So, so that is something we know, right? Um, okay, sorry, that is like something we know. Okay, so I think we can keep this, but only for an orthorhombic system. This part is only for an orthorhombic system, but it might not be true for, like, generally we take orthorhombic when we are talking about face-centered cubic or body-centered cubic. If you take the conventional unit cell, then it will be a cubic or orthorhombic unit cell. But if you take the primitive unit cell, it might not be. So the orthorhombic unit cell will satisfy this, but the non-orthorhombic unit cell will not satisfy that. So for an orthorhombic unit cell, G vector will have the mod. If you take this, then the G vector will actually have the modulus of 2 pi root h square by a square plus k square by b square plus l square by c square. This is like a simple algebra, or I mean, so we can actually like work it out a little bit. Is given as actually G dot G, and if you do G dot G, what you get is h star a star square plus k square b star square plus uh, L square C star square. So this is the mod of A star, which is just 2 pi by A actually, right? Or you can also write it as A dot A star. That is also something you can write it as, or like it's basically the same thing. Not exactly this. Sorry, A star dot A star. Yeah, A star dot A star becomes A star square. And the mod of A star is just 2 pi by A, or 2 pi by mod A. And if you do that, then you will get this h square by a square plus k square by b square plus l square by c square into, there will be a 2 pi term, because if there is a 2 pi term in front of every relation, there is a 2 pi term. So we can see that 2 pi h square by a square plus k square by b square plus L square by C square is equal to 2 pi n by DHKL for an orthorhombic system, only for an orthorhombic system. So this is a case study, orthorhombic case. So if you cancel the 2 pi's, what you get is uh, n by DHKL equals to h square by a square plus k square by b square plus L square by c square. And what happens when the orthorhombic becomes a cubic, or a equals to b equals to c? So it just becomes uh, 1 by a into under root h square plus k square plus h square. So by that, this relation will tell you that okay, the DHKLs we will get from the equation, from the the lattice spacing, right? that will eventually tell you what is A, what is the lattice parameters. So actually you can find DHKL from comparing multiple peaks, and by after doing that, once you know DHKL, you will be easily able to find out the A, or the lattice parameter. So that's how we find the lattice parameter in a crystallography, but that was a byproduct. But the main point of this video was to say that Laue's condition and Bragg's law, they're related, and if you relate them, you recover some very nice and intuitions, and you also, as we saw, that we get some practical equations by which we can actually read and infer data from the crystallography experimental data. So that was all. So see you in next class, where I will discuss more about crystallography, and I will discuss also about some experiments or some examples of how to read crystallographic data, and we will also go more into the structural uh, like properties like structure factor, form factor, because before going into rigorous calculations and the electronic models in the later parts. So see you in the next class.